Hello! In this video, I'd like to talk about non-standard models of the word logic. So what is the word logic? And this shows up a lot, but it doesn't have a real standard name to it. So I'm just going to call it the word logic. The idea here is that we're talking about words, and to a mathematician, a word is a finite sequence of letters, and letters just come from some sort of finite alphabet. In this case, we're just going to have two letters. We're going to have 0 and 1. And so when I talk about words, I'm talking about finite sequences of zeros and ones. And the structure that we're looking at is the set of all words with a prefix or equal to relation. So I'm going to denote this as prefix x comma y to indicate that x is a prefix of y. I'm going to have, this is a bit strange, but I'm going to have an operation that makes all of the characters in a word equal to 0. So, some sequences of zeros and ones, and we just make them all zeros, and it has the same length. And this is actually a tool that I'm going to use in order to capture the length of a word, right? Two words have the same length if when we zeroify them, when we make all of the letters 0, they wind up being the same when we do that. And then finally, we have operations to add fixed strings onto the end of a word. We can't take two strings, so sometimes you'll see plus. In this case, I'm going to use plus to mean word concatenation. We stick one word onto the end of another word. We don't have arbitrary concatenation, right? Given two variables x and y, we can't talk about x plus y. But if we have a fixed string, a constant string, we can tack that onto the end of a string x. So that is allowed, but taking two strings and concatenating them together, not part of the language. It turns out that we specifically can't talk about that, and we really want that out of the language, because if we can talk about concatenation, the language gets too powerful and too hard to analyze. So this is the structure that we're looking at. It's a bit of a strange structure, but it behaves just like any old mathematical structure. Words with these this relation prefix, this operation zeroify, and a whole bunch of operations to add fixed strings onto the end of a word. And we're talking about the first order logic of that structure. So I'm actually going to toss in, you don't really need these, I'm just going to toss these in for convenience, constants referring to fixed strings. We have, of course, the empty string, right? That's a finite sequence of zeros and ones. There isn't anything in the sequence, but it's still a word. It is still a finite sequence of zeros and ones. We have quantifiers, so we can say for all words x and there exists a word x. We have Boolean logic, and or not implies, all of that stuff. And we have equality, so we can say that two expressions represent the same word. So that's the logic, and from just this, we're interested in all of the different statements that we can form by combining these things together. So what sorts of statements can we form? Well, we can say something like every word is either empty or has a last letter, right? So for any word x, x is either the empty word, or it's the case that there is a word y where x is equal to y with a 0 tacked onto the end, or x is y with a 1 tacked onto the end. So not only does this word have a last letter, and we can figure out what that last letter is, but we can also cut off that last letter and look at the word that's left over. And we can also say that every word is empty or has a first letter. So for every word x, x is either the empty word, or the word 0 is a prefix of x, or the word 1 is a prefix of x. So these are things that we can say in this language. We're kind of combining everything together. Again, the variables are restricted. They can only talk about words. We can't talk about numbers because those aren't part of the structure. But we just combine everything together to produce any sort of formula that we want. What other things can we say? Well, we can say that any two words have a greatest common prefix. This is a little bit tricky to say greatest common prefix, but we can talk about a common prefix. We say for any words x and y, there is a z such that z is a prefix of x and z is a prefix of y, and then you have to go on to say, well, any other common prefix is going to be a prefix of this greatest common prefix. So that's what this second line here is for. But ultimately, we can say that any two words have a greatest common prefix. Any word has an all ones word of the same length, so a word where all of the characters are one, that's the same length. So here, again, we're using this trick with zeroify to say that two words are the same length. So, for any word x, there's going to be a word y. That's our all ones version, our oneified version of x. So x and y have the same length, and any prefix of y is either going to be the empty word or it's going to end with a 1. So that's kind of how we can say that y is a word of all ones. And of course we could say any word has an all zeros word of the same length, and that's the same as its zeroified version. There's lots of things that we can say in this language. It's a very robust language, and it's fun to kind of practice what are the things that we can say and what are the things that we can't say. So let's talk about the theory. So the theory of the word logic, and when we're talking about the theory of any sort of logic, we're interested in the set of all facts in the language that are true of the structure. Right, so all of the things that I've said before not only are things that we can say in the language, but they're also true things that we can say in the language. And so let's just collect all of those true things that we can say together to produce the theory of W, theory of the word logic. And one of the things that happens whenever you have an infinite structure and take its theory, there's some details you have to work out, but you can produce what's called a non-standard model. So a non-standard model of W, in this case, is going to satisfy all of the formulas in the theory of W, right? So all of the true things in the language, all of the true things in the logic that are true of words are also going to be true of this other structure, but it's not going to be an isomorphic structure. Right, so we have our word logic and we have our non-standard model, and they're going to be the same in terms of the facts that are true about them, but they're going to be different somehow in a way that this logic isn't going to be able to perceive. And it turns out, because of the compactness theorem, this is a theorem by Gödel, we can add to this theory an infinite number of statements that are finitely consistent. So any finite subset of them is consistent and consistent with the original theory to produce a new theory which is manifestable. And this is a tool that's used to produce non-standard models. So what we can do is we can add in a constant symbol, and we C, and say that 0 is a prefix of C, and 0, 0 is a prefix of C, and 0, 0, 0 is a prefix of C, and so on and so forth. Now, any finite subset of these is satisfiable where C is a constant that represents just like a really long string of zeros. But what compactness says is that we can actually produce a theory where infinitely many of these statements are true. And what that means is that C has to be some new infinite element for which all of these different words, 0, 0, 0, 0, 0, 0, and so on and so forth infinitely, are all prefixes of that word. And so let's think about this element C. Remember that we can say in this language that any non-empty word, and C is, it better be not the empty word, because there's only one empty word, and it certainly doesn't have any prefixes, or strict prefixes. And so any non-empty word is going to be some shorter word plus 0 or some shorter word plus 1, right? With some word with a 0 tacked onto the end, or a 1 tacked onto the end. And so what that means is that our infinite word we can cut off the last character, right? Our word C, we can cut off the last character, and we can cut off the second to last character, and we can cut off the third to last character, and we can cut off the fourth to last character, and so on and so forth. And of course, we can also talk about the first character of the word, which we know has to be 0 because 0 is a prefix of C. And we can talk about the second letter and the third letter and the fourth letter and so on and so forth. And so what that means is that our word C is actually going to have to be, it's going to have to be infinite. It has to be infinite because we've dealt with all the finite words. It's going to have to be infinite in the middle. And what this winds up looking like is something like this. So on the first line here we have kind of what C looks like. You have to add in a little bit extra to say that all of the prefixes of C end with 0, but that's fine. You can do that. That's just a sentence that you can write. And then here we can get rid of the last 0 and produce a new word that's also going to have to be in our non-standard model, because if you have a word, you can cut off the last letter, and that had better still be a word. And so if we have a non-standard word, we can cut off the last letter and produce a non-standard word. And similarly, we can cut off again the last letter, cut off the last letter, cut off the last letter, and so on and so forth. And of course, we can also add on, right? We can add zeros onto the end of C as well to produce even longer words as well. So these are some examples of things that are going to wind up having to be in the non-standard model, and this first element shows us what C looks like. So a bit strange. It's going to be infinite in the middle, right? We're used to things that are infinite on the tail end, or the integers, which are infinite on both ends, or the rational numbers, which are kind of like infinite densely. But this is something that we don't see very often, which is something that's infinite in the middle. But it's perfectly fine. Mathematicians, we can deal with that. And one of the interesting things is that we can use these words, which are all zeros, right? So words that are in the image of zeroify, to talk about positions in a word. And so here I'm going to introduce index notation. If we want to talk about the word at position Z, let's say that the character of word W at position Z is equal to 0, and it's not equal as words. It's just part of the notation. If there's a prefix of W that's of the same length as Z, and then we tack a 0 onto the end, and it's still a prefix of W. So depending on how you want to set up the indexing, you could say, for instance, that here we're talking about, the prefix of W of length Z, well, that either ends with a 0 or a 1, and we call that the character at that position. Here, just for notation and to kind of agree with the way that notation is set up in most programming languages, I've actually shifted everything over 1. So here, W of the empty word is actually just the first character in the word, according to this definition. It doesn't really matter how you set this up. Everything works out fine either way, no matter how you set up the notation. Maybe you have to fiddle with things a little bit in the formulas, but that is a possible thing to do, and the important question is what sorts of things can we say with these formulas, and not how complicated is it to say these things. So we can talk about the characters at various positions of words, and this includes infinite words, right? We can talk about, if we have an infinite word, we can talk about the character at an infinite position by using a word that's all zeros of that particular length to kind of get at that position in that word. And of course, we can talk about the character at a particular position being equal to 1. It's the same thing. And on top of this index notation, we can also do finite modification to words, right? So we can say that two words agree in all positions, except at this position, it's definitely a 0. And that's, here we have a formula that kind of says that in this notation. And a true fact of the word logic is that you can modify words at arbitrary positions. And so our infinite words, our new infinite words, also must be closed under finite modification, right? We can do this modification as many times as we want, any finite number of times, and these new infinite words, we have to be able to do this and produce new words. So our non-standard words, we have to be able to do this and produce new non-standard words in our model. And so what that means is that our words have to be closed under, when we're producing this non-standard model, our new words have to be closed under finite modification. And what that looks like, right? So we know that these are the words that we know are there already that have to be in this model. And what we can do is we can just take some finite number of these zeros and flip them to ones. So we now know that those things also have to be in the model. Although notice that if we pick one of these words and flip some finite number of zeros to be ones, then somewhere kind of, if we zoom in close enough, it's all going to be zeros again, right? You can kind of zoom in past all of the ones because there's only finitely many ones. So what sorts of things can happen kind of in this inside bit? Is it always going to be just zeros, or is there something else? It turns out that another thing that we can say in this logic is that we can describe a unique word, and first order logic can talk about things being unique. So there's a unique word of every length which starts with a 0 and alternates characters between 0 and 1. And this is how you could say that, for instance. And we can use these words, remember they're unique, right, of every length. So we can use these words to define whether a length is even or odd. And this includes our infinite lengths, right? We just use this formula and we see what happens, right? Because there has to be a unique word that alternates zeros and ones of this infinite length, and we just see where it ends. Does it end with a 0 or does it end with a 1? And, well, I'll show you a picture, right? So here we have C, right? It's this internally infinite sequence of zeros. And we know that one of these two words has to be part of the model. A word that starts off with 0 followed by 1, and then alternates 0, 1, 0, 1, 0, 1, and then continues alternating afterwards, after the infinite gap or jump, and ends with a 0 at the position indexed by C. And then we can also have a word that alternates zeros and ones, but ends with a 1 at the position of C. And these are two potential words that could exist. But what we actually need to do is we actually need to exile one of them to say, okay, there is a unique word of this particular length that alternates zeros and ones. So one of these two we need to add into our model, and the other one we need to exclude from our model. We need to make sure that it can never come into our model, because you can say in the first order logic, and therefore it has to be true of the non-standard model, that there's a unique word of this length that alternates zeros and ones. And what we're doing, in a sense, is choosing whether this infinite word C has even or odd length. And it turns out that, so using the same sort of construction that we did to talk about even and odd length, we can also talk about lengths, the remainder of a length mod 3 or mod 6 or mod whatever. And as such, we can say, so we can talk about this in the logic, right? There's a way of translating everything that I've said before to talk about whether a length is, congruent to 1 mod 3 or congruent to 0 mod 3 or so on and so forth. And so you can say things like any even length, which is congruent to 1 mod 3, is also going to be congruent to 4 mod 6 in the first order word logic, right? You can take this statement and translate it into that first order word logic to just purely, it's kind of gross, but you can write it out where where this is a thing that you can say in the logic, and it's true of the standard model. It's true of finite words, and so therefore has to be true of the non-standard model. And so as soon as we choose the remainder of C modulo 2 and modulo 3, we've also chosen its remainder modulo 6 by the Chinese remainder theorem. And that's, so how to say this? So the general Chinese remainder theorem is not a fact of the logic, right? We can't say that, you know, for all integers and there's, you know, some nice things happen with these moduli. But any specific instance of the Chinese remainder theorem, like this, can be translated into a first order logic formula and therefore has to be true of the non-standard model. And you can do some really silly things with this using compactness, because we can talk about lengths being congruent to 0 modulo whatever or 1 modulo whatever. We can add some really silly things into our theory using compactness. So let's add on that the length of C is congruent to 0 mod 2, and the length of C is congruent to 0 mod 4, and dot dot dot. And the length of C is congruent to 0 mod 2 to the n for every n, so that's an infinite number of formulas. And then we'll also add in the formula that the length of C is congruent to 1 mod 3. And this is a really kind of silly thing to do, right? It's a set of formulas that you can't find a finite C that does this, but any finite subset of this and all of the formulas that we had before, where was it? On this slide, so the formulas involving that 0 is a prefix of C, and 0, 0 is a prefix of C, and 0, 0, 0 is a prefix of C. So any finite set of those formulas and these formulas is manifestable by a sufficiently large C, a sufficiently large finite word consisting of all zeros C. And what that means is that we can make our non-standard model satisfy these properties. Right? By the Chinese remainder theorem, you can find a C that satisfies any finite subset of this and our original requirements on C, and so by compactness we can make C satisfy all of them. We don't have to. There's lots of different choices that we can make on C, and you can use this to produce a whole bunch of non-isomorphic, non-standard models, which is really cool. But I just think it's really cool that we can produce these sorts of silly remainder tricks where, you know, everything is finitely consistent. Obviously we can't have like we can't have, oh, you know, the length of C is odd and divisible by 4, right? You can't have that because that's not finitely consistent. But this set of formulas here is finitely consistent. That just means that any finite subset of it is consistent. And then you can again just use compactness to manifest the thing, which is quite fun. So what do the words of these models look like, right? What does our whole non-standard model look like? Well, so if we combine basic periodic words, right? So these words that, you know, start out with a particular configuration and then are periodic of some finite period n. And you can use bitwise operations to kind of combine these periodic words together in various ways. And then, of course, we have finite modification through a combination of these operations, right? The fact that our non-standard model has to be closed under these operations, we can show that our non-standard model must contain all of the words that look like, so here I just have C for reference. There's some, I don't know, some finite random sequence of zeros and ones, who cares what that is. Eventually the behavior becomes periodic, going into the infinite bit. The behavior is then periodic with the same periodic behavior matching up with however we chose how modular arithmetic works on this infinite bit. You know, everything has to line up based on our choices, right? We have to choose whether C is congruent to 0 mod 2 or 1 mod 2, and whether it's congruent to 0 mod 3 or 1 mod 3 or 2 mod 3. We have to make all of those choices. Once we choose it for one position, that determines the remainders in modular arithmetic for all of the other positions. And the periodicity going into the infinite bit has to agree with the periodicity coming out of the infinite bit. They have to be lined up, right? If there's a 1 in all of the positions which are congruent to 1 mod 3 going into the infinite bit, then there has to be a 1 in all of the positions which are congruent to 1 mod 3 coming out of the infinite bit for our particular choice of what it means to be mod 3 on the infinite bit. And then finally, there's some finite random sequence of zeros and ones, and this thing can be shorter than C, it can be longer than C, but it's going to look something like that. And in fact, this is it, right? So these words have to be part of the model, again, because we can produce these basic periodic words of every length, and so they have to be in the model. And because we can do finite modification, the finite modification versions of each of these have to be in the model. But it turns out that that's actually all you need. It turns out that if that's all you have, if all you have are these internally periodic words, then that actually suffices. And the proof of that, and this is really complicated proof, you have to, so given a formula about the standard model of words, we need to prove that it's true of this collection of non-standard words. And the reason why we chose this particular structure, this particular logic, is because any formula in this word logic can actually be converted into a finite state automaton. And then you just prove that the finite state automaton behaves as expected for these infinitely long words. So if we have some sort of input, and I don't want to go into details, but you have to use some sort of coding argument to be able to code if you have more than 2 states or more than 2 input characters. It's fine. It all works out. But essentially, you're saying that we have some sort of input sequence of characters, and we can produce a sequence of states that makes sense, that's consistent with the input and the transition function for the finite state automaton. So let's actually take a look at this. Here I'm just using a really simple automaton that whenever it sees an A, it stays in the same state, and whenever it sees a B, it switches between states S and T. And so this is kind of determining whether there's an even or odd number of B's in the input. In the standard case. It doesn't really make sense in the infinite case, but that's fine. We can still make sense of running an automaton on this particular input if we can find a sequence of states that forms a word that whenever we see a particular whenever we see a B, it switches from T to S, and whenever we see an A, it stays in the same state. And again, that happens on the infinite bit as well. And kind of the logic behind this proof is that, well, let's consider what happens if you run some sort of word like this through a finite state automaton. Well, we have kind of this random behavior at the beginning, and that's going to produce some random behavior on the states. And then eventually the input is going to become periodic. And at that point, we might have a little bit of a transition time, but eventually the states of the finite state automaton are also going to become periodic. And not necessarily periodic of the same period as the input. Notice that the periodicity of these states is 6, whereas the periodicity of the input is 3. So it's going to be periodic, but it might have larger period. But it's still going to have finite period because it's a finite state automaton. And then everything has to match up coming out. So the input is going to match up with the states, and that's all going to match up with, again, our choice of how modular arithmetic works for these on the infinite bit. And then eventually we're going to see some random string of characters again, and that's going to turn into a random string of states. So given an input, we can at the very least produce what we call a run, right? A sequence of states which is consistent with the input and the transition function of the finite state automaton, uh, uh, even though the timeline here is a little bit strange. So that works perfectly fine. The way that I like to call these words, I like to think of these words as a little bit like a candy bar, right? It's got these crunchy finite bits on the outside, and it's got these nice infinite periodic bits on the inside. So it's kind of like a candy bar. Um, Now, of course, you can throw in some more things into these non-standard models as well. So let's talk about this. Let's talk about other things that you can explore in this direction. And I guess the first thing that needs to be said about non-standard models is, why do we care about them? Well, the point of studying non-standard models is that it allows us to reason about what can't be said in the language, right? We have these two structures, right? We have the word logic and the non-standard model that we produced, and well, everything that you can say in the language that's true of one is true of the other, right? Every formula in this logic that's true of one is true of the other. They are not distinguishable via the language, but they're very different. They're very different structures. And so what that tells us is that the ways in which they are different cannot be expressed in the logic. And so it allows us to say things like, we can't say this in this particular logic. This particular logic is not powerful enough to say this thing. And so going back way to the beginning, when I talked about the fact that we didn't want to have arbitrary concatenation, being able to do x plus y, where x and y are words, to be able to concatenate those words together, we can show that you can't talk about arbitrary concatenation, because while you can concatenate any two finite words, you can't concatenate two infinite words in this logic and be able to in the non-standard model and be able to make sense of that. So what that tells us is that arbitrary concatenation of words is not a thing that you can talk about in this particular language. Although there are plenty of other proofs. So the fact that this language is kind of expressively equivalent to finite state automata means that we actually really know, we have a lot of really good ways of thinking about what can and cannot be said in this particular language. It's also very fun to explore these non-standard models. As I mentioned, we can ask questions. Well, so we can ask questions about can the, what sorts of patterns of letters can we have, right? We have one where it's infinite on the inside, but what if we want like 2 bits where it's infinite on the inside? Or what if we want infinitely many bits where it's infinite on the inside? There's lots of other questions you can ask about, like what sorts of positions can we have for these words? And you can also ask about can we do infinite words with aperiodic insides, right? So what happens if we throw in a new word that isn't periodic? Can we make sense of that? Can we throw that into our non-standard model and kind of be able to complete that into an actual non-standard model? And non-standard models are also philosophically very interesting. So, one of the questions that you need to kind of face when you think about non-standard models is, what if your model of ZFC or arithmetic, and these are, you can talk about these as first-order structures, and so it's non-standard models of things as powerful as ZFC or arithmetic are gross. They're a lot harder to study than this particular structure because we were dealing with a very nice language. But nonetheless, these structures do have non-standard models, and one of the questions you need to ask is, how do you know that your model is the standard one, isn't a non-standard model, right? How do you know that your natural numbers aren't actually somebody else's non-standard natural numbers? How do you know that your set theory is not somebody else's non-standard set theory? And this is kind of related to ultrafinitism, right? Studying non-standard models can help give you some sort of intuition for the perspective that ultrafinitists have. So ultrafinitists can say things like, oh, I have this, in my model of the natural numbers, you can start with 0 and keep adding 1, and you'll never get to 10 to the 100th, which is practically true, but in standard mathematics is not really true. But we can empathize with these ultrafinitists, because here I've produced a model of words for you, where you can start off with the empty word and keep tacking a 0 onto the end, and you won't ever get to this particular word that behaves like a finite word. We saw it as infinite, but it behaves like a finite word because everything in the model behaves like finite words, because we chose this non-standard model to behave like finite words, right? It has all of the same first order properties as finite words. And so I think that there's a really close tie between non-standard models and ultrafinitism, and I think that that's a useful thing to think about if you're trying to understand the perspective of ultrafinitists. So that's it. This talk is kind of a summary of some of the main ideas of my PhD thesis, which I'll link below. You're welcome to read more, and feel free to ask if you have any questions.